My name is Ian Graham. I'm a senior at University of Texas at Austin.
I'm Chris
But
Gomez. I'm a freshman, but going to be a sophomore at the University of Texas at Austin.
I'm Atul Tony. I'm also a freshman at UT.
Mr. Graham, what is your position at NASA?
My name's Lee Graham. I'm currently a planetary research scientist, but I've had, as I mentioned to you, 17 or 18 different jobs in my 35-year career at NASA.
Can you give a brief overview of the objective of the Altair landing project?
So the Altair lunar lander was created with the idea that NASA was going to try and do a different way of doing business rather than the big, huge bureaucratic government program with all these data deliverables and a huge team and a huge cost and 4, 5, 6, 7, 8 years of development time. So NASA decided to experiment and try a skunkworks approach, which is copyrighted by Lockheed, I might add, but pick, I think there were 22 of us discipline experts and move really fast and come up with a design that could fit in the schedule and budget we had. I was on the senior management team. I was the system engineering and integration manager. So my job was to, with a small team, develop the requirements, develop what were our goals, develop the processes for how we would work on the design and iteratively and come up with improvements. And so what we call closed architecture. So the final architecture fit within the limits of our mass and power and fit inside the fairing size even of the launch rockets and so on.
So it must have been difficult integrating so many smaller systems into one larger project. So how did you effectively communicate between the different design teams?
Well, so again, skunkworks is kind of unique, and especially at NASA, we were unique. We actually co-located everybody. So based on what Lockheed had done with their skunkworks, we brought everybody here to the Johnson Space Center for about 3 months and just got to know each other because most of us had never worked together before. We were all discipline experts in our respective areas. And then we got to know each other, set up the parameters, set up and actually went through the first design cycle to see, what did we come up with? What did it look like? And then we distributed it. We let the teams go back to their home centers, which were literally all over the country. Marshall Space Flight Center in Alabama, Kennedy in Florida, Jet Propulsion Lab in California, Ames in California. We literally had every single one of the 10 NASA centers involved in our project. So the biggest thing was communication. One of the disciplines inside systems engineering is called configuration management. So it was important that everyone was working on the same design. And as we discovered very quickly, if one team changed something slightly, it 99 times out of 100 rippled through the design. And so some other team, at least one other team, was affected. So what we saw was, for example, if the propulsion team wanted to add an additional 2% just for uncertainties in the orbit, that increased the mass of and volume of the tanks. So that affected the structures folks, which affected the loads folks. So they had to strengthen some of the attach points and added mass to the vehicle. And so there was virtually nothing we could change that didn't affect somebody else. So that was one of the things we worried about and communicated with everyone. The other one was we we designed the vehicle off of what was called design analysis cycles. So we would define, this is the parameters that everyone's going to start with. This is our goal to get to. This is the time frame. This is the resources, the money and time you have to do it. Let's go. And then, so we told everybody, this is what your goal is. This is how long you have to work on it. And then most of the times we never reached that goal, but we got close. So we would freeze that design, we would capture it and review it very quickly over a couple weeks, and then go into the next design cycle and start it all over again. So we were constantly communicating via email. We didn't have as many face-to-face meetings after that, but a lot of telecoms. So it was a big effort to keep everybody in sync and on board and progressing as quick as possible.
Wow. How long have you guys been working on this project?
So we got shut down eventually. We did get through the 4th design cycle, and we came up with a number which we're still not allowed to release, but it was extremely high. And so they said, well, we can't afford that, so let's stop. We worked on it for about 2 years. We were asked to capture all that information, and we did, and it's actually just been released with a procurement that NASA put out called a human lander system. And so SpaceX proposed, Blue Origin, in fact, they had a whole team that proposed. There was one team out of Huntsville, I can't think of their name, and then another team that proposed. And so they were given all our information as a starting point to use for their design.
So do you think the more updated space infrastructure that NASA has would make the project more feasible now?
Well, yes and no, typical aerospace answer. No, in that the physics haven't changed. You know, we were working with what are called hypergolics, so propellants that when they combine automatically burst into ignition. They're storable for long periods of time at reasonable temperatures. But we also we're using liquid oxygen, liquid hydrogen. Those are the most efficient, what we call highest specific impulse, but most efficient propellants, chemical propellants that we know of today. And so the physics haven't changed on that in like 50 years. So there's not going to be a whole lot of improvement on what we came up with. Electronics are a little bit lighter, but what we discovered in the design was electronics were like 2% of the mass. So it's not going to make a huge difference, you know, with the microelectronics that we have today versus 10 years ago.
So were you satisfied with the final project, like the result?
Oh, that's a loaded question. I was very happy with the team. We, like I said earlier, most of us had never worked together, so everybody came in with a desire to succeed, and it showed. And so everybody put in the extra amount of effort. No, in that I think we could have done another iteration with some out of the box ideas and potentially got the architecture to close. So one of the problems we were dealing with was the vehicle was a little bit heavy for the launch vehicle that we were talking with, that we had, and it wasn't as reliable. It didn't have the redundancy that we typically expect for a human crewed vehicle. And so, so we were working on adding additional backups and redundancies. The main issue I had was on the 4th design cycle, we had designed it, we had put in the requirements to match the Apollo lunar lander. And so it came close to closing. If we would have tweaked it a couple places, I think it would have closed. But we were already talking about the 5th design cycle to add additional redundancy, which adds mass and complexity. So we were starting to move in the wrong direction away from our goal. So that was a little frustrating. What we discovered very quickly in fact, before the even first design cycle, NASA has grown extremely conservative and risk averse. We did a very unusual thing in the entire Altair team, all 22 of us, went to Long Island, New York, and talked to the Grumman Aerospace guys that had built the Apollo LEM. And if you ever get a chance to read the history, it's just fascinating. But their company had a history of building Navy fighter planes that were very robust, used to slamming into decks, and very heavy. And so they had come up with this idea for a lunar lander with this chief engineer pushing it, and it worked. It fit within the limits that NASA had called for, and they ended up being selected. In fact, he famously told his crew when he called them together to announce that they'd won, he said, "Well, the good news is we've won. The bad news is we've won. Go home and kiss your wife and have a good meal, and then come back and don't expect to see them for 2 years." And it wasn't much of an exaggeration. But we learned from these guys, what their level of risk was, and it was just absolutely mind-blowing for us, and to this day still is. They went into it with the idea of, well, let me back up and give you some background. So for aerospace, we'll do what we call qualification testing. And so we'll basically say it's got to be in space for a year, and it's got to withstand this many thermal cycles and so on. Well, we'll qualify it for 4 times that, for 4 years. And then that's our quote unquote qual unit, which never flies. We just put that on the shelf. And hopefully it passed all the tests, which says the design is very robust. So then we bring in the flight unit, we put it through what's called acceptance testing, which are much more reduced spans or load levels or whatever the test is. And it passes, and we say, okay, we're ready to fly that. We have not worn it out. Well, what these guys did in Grumman was they said, we're going to design our qual unit and test it. And then we're going to go beyond that. So instead of, let's say, showing it 4 times the thermal cycles it would see in 1 year on orbit, or 2 weeks on orbit in their case, they would say, okay, we're going to take it to qual limit, and then we're going to take it beyond. And they would actually take it till it broke. And they took everything to the breaking point. And that, to this day, has never been done by aerospace. But they wanted to make sure they knew exactly how far they could push their hardware. And so they would come in, the project manager, who at the time was 93 when I talked to him, still totally alert, said he would go into a vice president and said, well, you're probably going to hear a bang today, but that's okay because we're trying to break it. And so if it broke, if they heard the bang, they'd say, okay, it broke where we thought it would, we understand. If it didn't break and stayed intact, they'd say it's way over design, and they'd thin out, something, make it lighter. If it broke early, then they'd add something to it to make it thicker or stronger. And so I asked them, I said, so, it worked for you, obviously, worked for you, your team, but how did it help NASA? And the project manager and in fact the whole team just looked at each other and smiled and turned to me and said, you remember Apollo 13? And I said, yeah, the LEM brought the crew back. He said, we were way beyond qualifications, but we knew exactly to the decimal how far we could push that lander. and that's what got our crew home. So that still has never been done to this day, but it was something that I'll never forget.
Would you implement a similar design process for your projects?
Yeah, it's actually, that's pretty standard with NASA. We have a document that's, the number is NPR 7123.1. I think it's up to C, version C now, called the Systems Engineering Procedures. That's pretty standard. What the thing that we did that was a little different was we did it very quickly. So we would do it in a month, what would typically take NASA 8 or 9 months. But yeah, I would do it again because it lets you pretty rapidly figure out where your problem areas are and where you need to focus your kind of limited resources in people and time and money. The lander got launched by a big rocket, actually bigger than the Saturn V. And so it would see, 6 Gs. And so the structure had to hold together under 6 times its mass, along with vibration, pretty significant vibrations, along with acoustic energy. So most people don't think about it, but even at supersonic speed, there is acoustic energy coming through the structure, and it's echoing inside the fairing. And sometimes it can get extremely high levels, it can get very loud, and it can start exciting the hardware. So that tended to make the hardware very heavy. I was lucky enough years ago when I was at the Naval Research Lab as the deputy project manager for another vehicle called the Interim Control Module. We were getting set to do an acoustic energy run, acoustic chamber run, and I said I'd never, experienced those levels before, and they said, well, let's have you see what it's like. And so they gave me some great hearing protection and put me in the acoustic chamber and went to about 130 decibels. That's more than a jackhammer 6 inches from your ear. So it's extremely loud. Now, oftentimes the launch environment can reach 170 decibels, and it's a log scale. So it goes up extremely fast. So that's a lot of energy. That put a lot of mass into the system, which drove up our overall mass. There were certain dense mass items that we had to model, like the engine, the descent engine, the ascent engine, were extremely dense, very heavy concentrations, as you would expect. And so we actually modeled them with point masses at their center of mass. And then we would sit there and try and balance the vehicle on ascent, which would also add mass because we'd have to put actuators in and that sort of thing. So lots of things drove the mass up.
And you mentioned that NASA is now a lot more conservative with the risks that they're willing to take. How do you think that will affect future design projects?
Oh boy. So we have a procurement out right now, and hopefully we're going to, let's see, it's the middle of April. In about a week or two, we're going to announce the winners for who's going to provide the next lunar landers. One of the approaches that we're taking right now is we're procuring the landers from commercial folks. I had an argument with a space shuttle program manager years ago that the commercial folks were going to go past us and start making advances faster than we could because we were so conservative and risk averse. And his comment was, Lee, there's no way that's going to happen. NASA's the only one that can fly humans in space. And this was 15 years ago. And I said, we're the only ones now. But at that time, I counted up, there were 200 people, 199 people, organizations that were working on human space flight. Some of them were simple, like there was a guy in Canada that was building a V2, a copy of a V2 German World War II missile with just a seat in the top, you know, so it wasn't going to be very rigorous. But I said, you know, only NASA is encumbered with all these regulations and requirements and risk aversion. These folks are going to pass us. And so now we're looking at buying, you know, we're already buying cargo transport to the space station from the commercial folks. Very quickly, in a matter of months, SpaceX is probably going to launch a couple NASA astronauts to the space station. And so now we're looking at procuring human landers from the commercial folks. So one way to avoid it is just to go around NASA and to buy it from the commercial folks who, you know, have deemed it good enough. And NASA says, yeah, it's safe enough. It's riskier than what we wanted to do, but it's still good enough. So that's, I think, one of the more optimistic points of the future is buying this stuff commercially.
So you said like everyone in the project was from different areas and all around. How do you think the different diversity to the group impacted the project?
You know, it was men and women, it was young and old. We had several astronauts. You know, with the diversity, it actually made us stronger because everybody would come at it from a different viewpoint. We had folks from JPL that had experience in unmanned vehicles. We had folks like me that had worked on space shuttle and space stations. So I had a lot of crewed experience. We had crew that had actually flown. Diversity, without a doubt, in my mind, made us stronger. We had people that had just come out of college. We had people that had, you know, 30 years experience. So it was a really nice mix, and it was a great learning environment. Everybody had a desire to succeed. So everybody would put in the extra time and spend the time explaining their design. So everybody learned from it. It was a great experience.
Thank you so much for talking to us.
You're welcome. Good luck on your school career. I think you've chosen a great university, so I think you got off to a great start so far.